Thanks. Okay, so it's great that you're still here at the last talk. I'm going to talk about optimization, so it's quite a bit of a different topic maybe. And just to give the talk a little bit of structure, first I'd like to talk about the basics of greedy optimization, especially about gradient descent and stochastic gradient descent, and also quickly explain what does stochasticity actually means and like where it comes from. And then the most part of the talk I'd like to talk about how we could robustify stochastic optimization. And I'm going to talk about the specific example, which is step size adaptation. Okay, so this is the general problem setting. Oh. So imagine you want to optimize a function L, and you want to find any local minimum x star. And what a greedy gradient-based optimizer does now is it has an estimate xi of this local minimum, and then it updates that estimator by iteratively descending downhill somehow. And for this descent, it has a loop, and in the loop it has normally two steps. And the first one, so it's positioned somewhere, and the first step is it decides which direction it wants to go. And then after deciding which direction, it asks itself how far do I want to go in that direction. And this is the step size. So basically at each step of the optimizer, you have to make a decision about a vector S and a scalar alpha. And then you repeat until your budget is full. So that sounds pretty simple when you look at that. But now imagine you're writing a piece of code and you're distributing it to people. And every person who uses this has a different L. But ideally you want this thing to work for all kind of L's or a reasonably large variety of L's. So actually inside of a simple optimizer that you probably use every day or very often without thinking about it, there's a lot of things going on. So S and alpha have to be different depending on L. And all of this has to be done automated. Okay, so at each step, S and alpha have to be adapted or learned or somehow inferred depending on what you get from L. So what you get when you evaluate the functions. So functions, function values and gradients basically. Okay, so this whole thing inside is actually doing something very smart. Okay, and in the talk mostly I will focus on the second line here. So we will just say someone gives us a search direction, and we're left with the decision of how far we want to step in that direction. Okay, but just because also many people are from the summer school, a quick introduction to how this thing actually looks when you plot it. So imagine your function is two-dimensional. So this is the Brownian function, and it has a minimum over here, and your optimizer starts over here. And now you evaluate the gradient. So this is then your search direction would be just a negative gradient. So that's like the easiest you can think about. It's just the steepest way downhill. And so the search direction, you set it to the negative gradient. And alpha could just be constant. So you can just set it to 0.1 or something. And then you evaluate the gradient, multiply it with 0.1, and make a step. And then you do the same thing over and over again until you hopefully arrive at the minimum. Okay? So that's the basic concept. There's sometimes one additional difficulty, which is that we do not know the gradient precisely, or we do not know the function value precisely. And then this thing is normally called stochastic optimization. And there's one reason why this happens, often because your L, so your loss function that you want to minimize, is actually a large sum. So people who train neural networks know that, for example. Then capital M would be your number of data points, for example. And this can be some millions, so when you think of ImageNet. And this is actually not feasible to evaluate each time. It would just take too long. And so what people do is they approximate this function and its gradient by just a smaller sum. So you subsample. So you have some index set j, and you take that randomly from your whole index set. So m is very small. It's maybe 10 or 100 or 1,000. And then this you can evaluate very fast. But the problem now is that L hat is not exact anymore. It's an estimator. And the gradient as well, because differentiation is just a linear map. And this estimator is approximately Gaussian distributed because this thing is the sum of random numbers. Okay? So we have an estimator with approximate Gaussian noise. Okay, so that's how it looks if you run the exact same algorithm as before, gradient descent, but your objective function returns an imprecise number. So now you call it stochastic gradient descent. But when you look at it from the perspective of an optimization or of an optimizer, of the code of an optimizer, nothing actually changed. Like you're running the exact same code, you're just calling the function and updating according to the negative gradient. So the optimizer itself has no idea it's running stochastic gradient descent. It's still a gradient descent. Okay?
One, could you speak up a bit so that we can understand you a bit better here and back? And the second would be, is it the same step size?
Yeah, no, it's a bit smaller. So I come to that because I'm going to talk about step size adaptation. But normally, the higher your noise is, the more cautious you have to be approximately. Yeah. I don't remember the numbers. I can look it up. But maybe now it's 0.01. Yeah, so you lose in efficiency, but therefore also your function evaluation is faster. So maybe overall you might actually be faster than if you evaluate the gradient completely. Okay, so that's stochastic gradient descent. Oh yeah, and another point which is maybe important is that the algorithm is completely deterministic after we've chosen your mini batches, like after we've subsampled your mini batches, right? Because you get always exactly the same update and exactly the same function evaluation. So the randomness doesn't happen inside of the optimizer itself, but just inside of the function evaluation. So when you hear stochastic optimization, normally the code is not stochastic. It's just the function evaluation that is stochastic. Okay, cool. So what I've shown you, alpha was constant and hand chosen. And now we normally don't want to do this because we just want to press a button and run our optimizer. And we don't want to be concerned about setting parameters. So it would be great if there was some little algorithm inside of the loop that would do that automatically. And it turns out that it already exists. And this thing, they're called line searches. So just again to illustrate, let's say you have a finite budget, which is, I don't know, 20 steps, and you choose your step size too cautious, then it might be that you just don't arrive. So your optimizer is stable and it makes progress, but it's just not enough progress. So you think I can crank up the step size a bit, but then what happens is you get unstable. And now this is sometimes very fiddly. So sometimes an optimizer is stable when you choose the learning rate as 0.014, and it's unstable when it's 0.015. Okay, so it's sometimes super tricky to find this, and also it's actually not clear at all if a constant step size is actually a good thing for a nonlinear function, because it might just look very different in different regions. So then you would have to do hand-tuned learning rate schedules, and it would take you very long to do this. So the solution are, or one solution are line searches. And that's a pretty clever algorithm. It runs inside at each step. And for example, here it makes a quite long step, a bit of a shorter one. And it actually arrives at the minimum in like 4 or 5 steps only. So that's pretty perfect. Why don't we also use this for stochastic optimization? And it turns out that it just doesn't work there. So line searches are around since a very long time, basically since BFGS was invented. So I don't know how long, but maybe 50 years. But as soon as we have this problem that we only have L hat and not L, we can't use them anymore. So we need a new one. Okay, so basically the rest of the talk will be like this, that I quickly introduce one concept of line searches that work classically, so without noise. And then we're going to translate this concept one-to-one into a probabilistic setting where we assume that the data points, which are now the gradients and the function evaluations, are corrupted by Gaussian noise. Okay, so now this is the plot for the classic line search. And we're going to step through it one by one to just understand how this algorithm works. The first thing, important thing is we're always one-dimensional, because after we've chosen the search direction, we're just walking on one line and have to find a scalar. So our approximate or our optimization problem that we have to solve approximately to find like an approximate minimum is one-dimensional. So up here is the function value in that direction. This is the projected gradient in that direction. And t is the step size. And I've marked green areas up here and down here. And they are areas which are good. So areas where we say, OK, when we step there, the point is fine. And fine is encoded, or acceptable is encoded in the Wolf conditions. They're also around since a very long time. And they just make sure that, so the first Wolf condition makes sure that your function value decreases, at least a bit. And the second Wolf condition makes sure that your gradient gets flatter. So you want to get into a region where you decrease the loss and where your gradient gets a bit smaller. So that makes sense. OK, then the line search just tries out one initial step size. So it's going to evaluate here. It finds a value. And it will not accept this because the gradient is not inside of the green region. So it's just going to try further out to the right because the gradient is still negative, so it knows it's still going downhill. So it's going to do one extrapolation step. It evaluates there. And now it finds that the gradient is positive. So somewhere in between there must be a minimum. But now the function value is too high. So to the right of here, probably there's nothing to look at. To the left, either not. And now it's trying at the local minimum of some curve that you lay through here. And this is just some polynomial, maybe a third-order polynomial. It evaluates here again. And now this point lies inside the green areas, and it's accepted. So that's the basic concept of a classic line search. OK, so in summary, the classic line searches, they model the one-dimensional objective with a cubic spline. Then they search for candidates by first extrapolating and then stopping and going backwards. And the third thing is the Wolf conditions as acceptance criterion. Now we're going to translate this thing to the setting when we have noise. So instead of cubic splines, we're going to use a special Gaussian process which has where the mean are cubic splines. Then instead of collapsing the search space for suitable candidates, we're going to do some kind of lightweight version of Bayesian optimization. And instead of binary wolf conditions accept or not, we're going to have some probability that wolf conditions are accepted. Okay, so the GP we're going to use is an integrated Wiener process. And the kernel looks a little bit cryptic, but basically it's the process that just assumes one derivative. And the means are cubic splines. And therefore it's very robust, but also still very flexible. So you can think of it as the straightforward extension of a third-order polynomial to the probabilistic setting. And the nice thing also, it has, as like a third-order polynomial, it also has analytic minima. Then for the search for candidates, we use Bayesian optimization. And when you do Bayesian optimization, you have to choose some acquisition function, and we use the expected improvement. But we're not going to optimize this expected improvement globally, but we're just going to evaluate it at a few well-chosen candidate points and choose the best one from them. Okay, and the third thing that we need is the wolf conditions. So when you read, these are the weak wolf conditions I've shown at the beginning, so the acceptance criteria. And you can rewrite these two formulas in this way, such that it's an inequality for A and B greater than 0. And A and B is a linear map over function values and gradients. And we have a Gaussian process surrogate over the function values and gradients. And because this is a linear map, we also get a, or that implies a GP, the GP implies bivariate Gaussian distribution at every step size over A and B. And we want, for the wolf conditions to be fulfilled, we want A and B to be positive. So now the probability that wolf conditions are fulfilled is the integral over P over the positive quadrant. And we're going to accept a point now if it's just above a threshold. Okay, so now this is the step-through algorithm now for the probabilistic line search. It works very similar to the classic one. What plotted here on top is the marginal over the function values of the GP. And here in the middle, it's the marginal over the gradient. And so it works very similarly. It first tries at some initial candidate. It evaluates. And it updates the GP. So you can see here it's a bit more certain. And what you've seen down here, this is the wolf probability. So this two-dimensional Gauss blob here is the probability density for the wolf conditions. And for this thing to be accepted, we need it to lie inside of the screen area to at least some percentage. And we've fixed it to a certain value, and we decided it was 30% for not to, yeah. So this one doesn't lie in there, so this point is for now rejected. Then the algorithm tries to extrapolate again, evaluates, updates the GP, and again checks this point. And this one just lies to about 7% inside of the green area, so we also don't accept it for now. And now we have two candidates. One is another extrapolation point, and the second candidate is the local minimum of the posterior mean. So here you can see it goes through 0. It's a local minimum. So this is very similar to the classic style. And then we want to decide where we want to evaluate actually. And the curve, this thick blue curve, is the product in between the expected improvement and the probability that the Wolf conditions are fulfilled. So we will just evaluate the thick blue curve at these 2 points, so here and here. And then we compare these 2 numbers and take the one with a higher value, and we evaluate there. So in that case, it's the local minimum. And then we check this point for acceptance, and here there is enough probability mass inside the given area, and that's why the point is accepted. Okay, so in summary again, we went from a classic line search to a probabilistic one by just translating each component to the language of probability. The first one is, instead of cubic splines, we used a GP with where the mean is a cubic spline. Then the search for candidates, instead of making hard decisions and collapsing search space, we use Bayesian optimization, or an approximate version of it, a lightweight version of it. And the acceptance is, instead of the binary Wolf conditions, we use the probabilistic Wolf conditions, which are a very natural extension to the classic Wolf condition. Okay, and that actually robustifies our optimization problem, so we don't have to hand-tune learning rates anymore. So what I've done is we've trained some neural networks. So the left plots here are for Cypher 10 on a 2-layer neural network, and the right one is on MNIST. And we've just started the algorithm once with fixed learning rates. So this is the test error performance versus the learning rate we started it with. And the performance depends very, very much on the choice of this learning rate when you just keep it fixed. And the SIG lines, that's the performance when you use the line search and when you initialize it. So the very first step is the learning rate, which is indicated here. So it kind of is it's insensitive to the choice of this initial learning rate, and it just adapts the step size over time. So the bottom plot is basically the same, but in the evolution in time. So this is per epoch. The left plot is always for the fixed learning rates. So the performance is kind of has a high variety. And for the line search, it doesn't matter how you initialize it. It just always gives you the same. And the error bars there over multiple runs with different initializations. Okay, so I hope this came across a bit, that optimizers inside actually learn quite a bit. So they can learn the step size. You can also, so the data they take in their likelihood is then in the end the gradients or the function values that are noisy. And the prior that you use tries to encode the structure of the objective you use, and you on the fly learn its hyperparameters. And then it can infer many things. So for example, the line search infers an approximate minimum each time. You can also think of, like, you can make this field much broader and maybe think of, actually I can maybe infer more robust search directions if I tell the code, this is your gradient, but it has this and that Gaussian noise. So if the code is not only called stochastic, but if it actually has a number in there, which tells it, I can rely this much on my gradient and this much on the model. And there's, of course, a lot to do still. Maybe just to give you a bit of a hint, it's actually possible to also interpret classic search directions like BFGS as map estimators of Gaussian inference. And going from there, we can actually, so these map estimators have a likelihood which is a delta peak, so there's actually no noise information in there. But going from there, we can say what happens if this likelihood is not a delta peak anymore. It's a Gaussian distribution. Then eventually we can infer more robust search directions, because everyone knows that BFGS goes nuts when I don't use it with exact gradients. Okay, so because I know some people are interested in this, a very cautious advertisement that Lucas, who is sitting there, implements our stuff in TensorFlow, and hopefully soon we'll release some stuff about it, because we have a lot of requests that people want to implement things, and it's quite hard to do by yourself. So maybe if you wait a bit longer, we're gonna have something out soon. And if you want to know more about also specifically the implementation, because I think it's also a slightly bit different than what I told you right now, have a beer with Lucas. And other than that, you can also ask me. And thank you.
Questions? And how does this compare to other standard optimizers in TensorFlow, such as perhaps Adam or Algebra? Is it competitive to those?
So the idea is that, it's a good question, by the way. The idea is that you can use these on top,
Okay,
right? So you've chosen your search direction, and then if you want, in front of it, you can put this line search,
Okay.
and maybe your Adam will become even better.
Okay, by choosing parameter more
Yeah, or more precisely. I mean, Adam, you also choose some parameters somehow a little bit, yeah. But it might benefit from it if each time the step size is adapted on top of that.
Michael?
You said that for further directions that one could learn the search directions. Can you elaborate on that?
Yeah, so
What do you mean?
basically, you can just think about that you, for example, want to model a second order search direction, and then a second order search direction. And so you have a model how your second derivative maybe changes according to where you are. So you have a Gaussian process
So
as prior.
Here it's nice because you're dealing with univariate quantities, and as soon as you're incorporating the stochasticity of the gradient, you have a multivariate random object.
Yes.
So how much more difficult does it then get?
Yeah, so it turns out that it's really feasible, and the hint I can give you is that BFGS or LBFGS is actually a map estimator. So once you've written down the math, you see that these things are actually super efficient and it's possible. So they choose a very specific covariance. I can point you to a paper. And by choosing this very specific covariance, their update is, or the map estimator is exactly the BFGS update. So it's.
Because at the end they nonetheless work then with projections, so then one has more one-dimensional random quantities again. Is that perhaps the trick? So I think in the updates you sometimes then take inner products between the noisy gradient and some
For the
other
line
quantity.
search, you mean now?
For the limited memory update steps, for example.
Yeah, I mean, if you do a limited memory BFGS, you have, but it's still order of n. So if n is your dimensionality of the problem, you have maybe 10 times order of n or something, but it's still order of n, and that would be similar. So you gain a lot because every step is more efficient. So overall, you have to, in every step, you always have to say cheaper, such that in the overall optimization progress, you're still better than if you just run stochastic gradient descent. And it's definitely feasible to do it.
Okay, then Alan.
In case the function evaluations are expensive, not only the size of the data set.
Sorry?
In case if the function evaluation is expensive, is there any trick that you can apply, or this thing applies only if your data set is large?
So,
Did you get my question? So I mean, The cost function maybe is expensive, right?
Yeah.
Sometimes. So in this case, is there any trick that you can apply such that to, I don't know, tackle this problem or perhaps skip these steps? Like
Yeah. So what you're asking is basically, is it actually feasible to use such an optimizer if my evaluation of the function is anyway very expensive? Yeah, but that's a question then if you want to use this gradient-based optimizer after all.
Yeah, I mean, in some cases, it's the only way that you can use the gradient set because you cannot compute the Hessian, for example, or something else. But the function itself is expensive because you have to make a lot of computations or I don't know, something else. So is there a trick that you can apply such that to tackle this problem, like to not evaluate the function many times, but just sometimes, such that to have let's say, fewer evaluations?
So just that I get it correctly, you mean the function evaluation is hard, but the gradient is cheap? Or what do you mean?
The gradient is expensive, so I mean, don't copy the gradient many times, but...
I mean, do so are you saying that in cases where stochastic gradient descent is not applicable anymore, or is it a question about the line search? I'm not quite getting it.
That's later.
Okay.
When you're using the integrate Reno process.
Yes.
Does that have any hyperparameters that you need to
Yes.
fix? Is it sensitive at all to the choices that you use? For that?
Yeah. So
Depends on
for each step, the hyperparameter is adjusted. So it changes on the fly, basically. So that also basically when you do optimization in general, there's always this underlying assumption that your function is somehow is somehow varying slowly, right? Because otherwise, no method that eventually has a constant learning rate or something would work. And it's done like that. So it learns something like a length scale that changes over time.
At the beginning, you start off with just a single point.
Yeah, you start at basically the point you start off with is that one.
Yeah.
It's just the initial one. And then it adjusts it learns the hyperparameter, but it doesn't stay fixed. So at every step, it changes it slightly such that the hyperparameter adapts over your optimization run.
I'm just wondering, like, you have the expected improvement available. So if you use only the expected improvement to optimize it, whether that's gonna, comparatively, is it performing better with this additional line search or not?
So we're using the expected improvement inside the line search as to check which of the so basically we're telling the line search this would maybe be a good point to try out and this would maybe be a good point, and then the expected improvement just compares them and says, oh, this one might be better because probably the function value is lower. So that's how we use it.
So on the other hand, you can think of just using expected improvement to sort of...
Or just do global optimization. Yeah.
Just the
exactly, yeah. But
I may have missed that.
So that's a really good question. So we did it like this because line searches have to be super efficient. So actually what you want to have, so each function evaluation is expensive. So you want to do as little as possible. And what you want to do ideally is that the line search doesn't interfere at all if the point is good. So you evaluate once, and the thing just checks some Wolf conditions and says, yes, good, and goes on. And in the end, that's also what it does in 80–90% of the steps. It just accepts. And only if the step is very wrong, it should evaluate once more and waste one function evaluation. Otherwise, you're much less efficient. So let's say if already each line search wasted 2 or 3 evaluations, we would never be able to beat stochastic gradient descent. So this thing actually is like a governor. It's not deciding something actively all the time. It's just saying, okay, this step was super bad, or it's like just slowly increasing the learning rate. So that's why we do that. Otherwise, so that's why there's this acceptance criterion. Yeah. Oh yeah, maybe one more time. It's also maybe good to know that a line search is not better if it finds an exact minimum. It should, because you can, like, the optimization progress is always measured after it arrives, like at the end, after a week, after you've trained your model. So at each particular step, it might maybe help you to find a very good minimum, but in the end, it didn't help the complete optimization progress if you were very exact. So that's why we have these wolf conditions that say this is a good region and we want to be in there, but the precision is not important.
Okay, so let's thank Maren again.